Welcome back to another episode of Once Upon a Lecture. I'm Princess Elsa, and today I'm going to be teaching you about graphing data in statistics. On our agenda today, we're going to first talk about some graphing basics. So before we start making our own graphs, there are certain rules that we need to follow and that we need to learn in order to actually start creating graphs of our own. We're then going to talk about what is called the normal curve. Many of you may be familiar with the term bell-shaped curve, so we're going to talk about that curve, also known as the normal curve, and see how it relates to graphing data. The next thing we'll talk about is skewness and kurtosis. So anytime a distribution deviates from the normal curve, we tend to say that the data are skewed. So that's what we'll talk about when we talk about skewness, and we'll also learn about kurtosis, which refers to how peaked or flat a particular graph is. The last thing we're going to do is talk about the different types of graphs we see in statistics, and we'll even get to create some of our own together. Let's get started. You may be asking yourself, what is the purpose of using graphs in statistics or mathematics? Well, let's think back to the old cliche phrase, a picture is worth 1,000 words. When we look at a large amount of data, it's often easier to illustrate a large amount of information with a picture instead of using a lot of words or numbers and tables. So, graphs help us organize a large amount of information into a concise illustration. A graph is typically composed of a vertical line, which we call the y-coordinate, and a horizontal line, which we call the x-coordinate. Now, the y-axis should be 3/4 the length of the x-axis, which means the horizontal line at the bottom on which you plot your x-axis should be longer than your vertical line, your y-axis. Additionally, when you create your graph, you need to know that the numbers have to be placed in equal intervals along both the x and the y-axis. So what do we mean when we say equal intervals? Well, let's say typically we start a graph at 0. From 0, you will increase, for example, 2, 4, 6, 8, you will increase in intervals of 2. Or you can increase in intervals of 3, 0, 3, 6, 9, etc. It all depends on the minimum and maximum data points you have in your data set. What you cannot do is not use equal intervals, which means jump from 0 to 2 to 7 to 12 to 35, 42, right? So each interval has to be equal for both the x-axis and the y-axis. Typically, the independent variable is represented along the x-axis and the dependent variable is represented along the y-axis. So if you remember back to our previous lectures, I believe with Princess Jasmine or Princess Ariel, they taught you about the fact that the independent variable is typically known as the cause in an experiment, and the dependent variable, which we plot on the y-axis, is known as the effect. If you are plotting numbers for a frequency distribution, for example, you will have a score and you want to know how many people got that particular score. In that case, you would have the score on the x-axis horizontally, and then the frequency, the number of times that score occurred, plotted on the y-axis. But don't worry, we'll be doing some examples together to ensure that you understand what this means. So, we talked about some basic rules for graphing, right? We talked about having two axes, we talked about having equal intervals along both axes, and we also talked about the fact that the y-axis needs to be 3/4 of the x-axis. So what happens if these rules are violated? Well, data can actually be misrepresented and you can actually be accused of data fraud. Nobody wants to be accused of data fraud. So it's very important to understand how the increments can affect whether a change is visible in your graph or not. The larger the increments that you use, the less visible the change in data will be seen. Conversely, the smaller the increments you use, the more visible the change in the data will be seen. I know what you're thinking. What is Elsa talking about? Don't worry, I'll show you right now. Let's say we wanted to see the change in interest rates for houses in Arendelle between 2008 and 2012. By looking at this graph, do we see a change or not? You may notice that in 2008, the percentage is 3.140. By 2012, it's 3.154. The difference from 3.140 and 3.154 is not a large one. However, by looking at this graph, we can actually see the growth in data because the intervals on the y-axis are very small. Now let's look at this graph. So in this graph, we see the same data points and we see the same years along the x-axis. So by looking at this graph, do we see a change or not? If you're thinking to yourself, no, you don't see a change, you're absolutely right. So let's take a look at the y-axis. If we look at how this graph differs from the previous one, we can see that the intervals along the y-axis are in 0.5%. So from 0 to 0.5, from 0.5 to 1 whole, from 1 to 1.5, etc. If you remember, the difference was between 3.14 and 3.154. So all of those are within the range from 3% to 4%. Here on this graph, the increments are way too big. Therefore, we are not seeing any visible changes in this graph. So again, the increments for the y-axis are too large and no change is shown. So you have to be very careful with the type of increments and intervals you choose to label your graph with. You could make a mistake by misrepresenting data in which you are showing that there is a big change when in fact there is not, or conversely, when you are showing that there is no change when in fact there is a change. So again, intervals are really important for when you set up your graphs. Now we're going to talk about the normal curve. So as I mentioned previously, the normal curve is also known as the bell-shaped curve. What is special about the normal curve is that it is absolutely symmetrical. When something is symmetrical, it means that if you were to fold it in half, you would have the exact same thing on one side and the other. So these things that are symmetrical are in fact data points. With the normal curve, it states that there is an equal amount of data points to the left and to the right of the center of a point of data. Now let's talk about this center. The center of a normal curve is typically the highest point. If it is the highest point, it means that it occurs the most often. That is what we know as a mode. Additionally, if we think about the rule of symmetry for a normal curve, if you have 100% of data points and you fold it directly in half, the middle would be the 50% line. So everything that is 50% of your data points to the left and to the right is what we know as the median. And furthermore, in a normal curve, the center point is the average of your data distribution. So in the normal curve, the mean, the average, the median, the midpoint of all your data points, and the mode, the score that occurs the most, are all the same number. So we know that there is an equal number of data points below the average or the mean, as well as above the average. So these are special characteristics that are relative only to the normal curve. Let's take a further look at what that normal curve looks like in terms of percentage breakdown of a distribution. So here we see the line in the middle. If you notice that symbol is mu. Mu represents a population average. You may also notice that mu, or the average, is the highest point in this graph. If you look to the right side of the average, you see that there's 34% of data points that make up that chunk colored in dark blue. What that represents is one standard deviation above the average. I know the word standard deviation may seem a little foreign to you, but in a couple weeks, I promise you will be very familiar with the term. All you need to know now is that on a normal curve and a normal distribution, you have data points that go up to 3 standard deviations above the mean and 3 standard deviations below the mean. So every sigma symbol that you see in the graph represents a standard deviation. So you have 68% of your data points that fall in the range of -1 standard deviation and +1 standard deviation. That means that the majority of scores in your distribution fall within 1 deviation below the mean and 1 deviation above the mean. As you continue going farther out along the extremes, you will notice that the scores that fall within 2 standard deviations above and 2 standard deviations below the mean are 13.6%. That is clearly less than 34%, which shouldn't surprise us because the majority of the scores are clustered around the mean. Furthermore, if you go even farther out towards the extremes, you can see that 2 standard deviations above and below the mean is a mere 2% of the population in your distribution. So again, the whole point here is to show you that in a normal curve, most of your data points will fall around the mean. The mean is also the most frequently occurring score, and it is also exactly in the middle of all of our data points of our distribution. So the question I have for you is, are data always going to be perfectly symmetrical? If I were to go out and conduct my own experiments, would I collect data that falls perfectly in a bell-shaped curve? Will most of my data points be clustered around the mean? So that is a great question, and the answer is no. Data are not always going to be perfectly symmetrical. So that brings us to our next topic of skewness and kurtosis. If the data are not perfectly symmetrical, we typically say that the data are skewed. Skewed curve versus a normal curve suggests that the scores are piled at one end or another, and the tail is at the opposite end. I promise I'll show you what that means in a minute. So we have 2 different types of skew. The first type of skew we have is a positive skew, in which most scores are concentrated below the center point. I know that seems a little bit backwards because if we say something is positively skewed, why would most scores be below? But remember, the term skew refers to the tail of our distribution. The second type of skewness we have is called a negative skew. When data are negatively skewed, it means that most of the scores are concentrated above the mean or above the center point. And the most important thing to remember is that the polarity, whether it's positive or negative, indicates where the tail is. So if something is positively skewed, it means the tail is on the positive end. If something is negatively skewed, it means the tail of our curve is on the negative side. So let's take a look at some examples. Here we see examples of skewness. If we look at the very first graph, we see that the mode, the most frequently occurring score, exists to the right of the mean. If something is to the right of the mean, it means it is greater than the mean. So here we can see that both the median, the 50% mark, and the mode, the most frequently occurring score, are both above the mean. In which case it suggests that most of the scores are clustered on the higher end of our distribution. Most of the scores are going to be higher than the average, above average. So the tail of our distribution ends up on the negative side, which means there are less negative scores. When there are less negative scores, we call that a negative skew. Now let's take a look at the second picture we have. This may look familiar because absolutely right, it is a normal curve. You can see that the mean, median, and mode, once again, are all the same number and are smack down the middle. Lastly, the last graph on the right-hand side is a positively skewed distribution. Again, positively skewed means the tail is on the positive end. If it's the tail, it's the low part, which means there are very few positive scores. There are very few scores that are higher than the average. Most of the scores we have are below average, which means the skew is positive. Once again, you will notice that the mode in a positively skewed distribution, the most frequently occurring score, is below the mean. It is below the average, as well as the median. So if the average is higher than the mode, and if the average is higher than the median, it's a good indication that you will have a positively skewed distribution. So again, I realize that this is a little bit cognitively dissonant because we're typically used to hearing positive means good, means higher, negative means lower, means worse. However, in skewness, they are actually flipped. So the polarity, whether it's positive or negative, is indicated by where the tail is. If you have a lot of high scores, the graph is negatively skewed. If you have a lot of low scores, the graph is positively skewed. And if you have a perfectly symmetrical distribution, you have a normal curve, and the skewness would be 0 in that case, okay? So when we talk about skewness, we are talking about symmetry along the x-axis. That's the horizontal one. So if I were to take a graph of my x-axis and fold it in, I can't do that with my arm, and fold it in half, right? That would tell me that everything, the same amount of data points on the left equal the same amount of data points on the right. So we're talking about symmetry horizontally. But we can also talk about the symmetry of a graph along the y-axis, right? And that is typically going to tell us how flat or peaked a graph can be. So when we talk about how high or low the peaks of a graph are, we are talking about kurtosis. Not sure if you've ever heard this word before you joined a statistics course, but it was definitely news to me. So kurtosis determines how high or low the peaks of a graph are. And we have 3 different types of kurtosis. The first one is platykurtic. I helped myself remember this by thinking of a platypus. And basically with the platykurtic graph, it means that the majority of scores are toward the bottom, which means you don't have a high peak. It's kind of flat against the bottom of your graph. Leptokurtic means exactly the opposite, that the majority of the scores are at the top of the graph. So it's going to have a higher peak. So that's leptokurtic. And then similar to a normal curve, when your kurtosis is evenly split between high scores and low scores, we call that mesokurtic. Mesokurtic means that the scores are evenly distributed between the top and the bottom. So let's take a look at some examples of kurtosis. In this graph, we can see 3 different types of kurtosis. The first one is called mesokurtic. So if you were to draw a line halfway horizontally through that distribution, you would have the same amount of scores at the top above the line and below the line. The second graph we can see is called leptokurtic. We can see that there is majority of data points occur at a higher peak. So whenever you see a high peak, you should know that that is leptokurtic. And the last example we have is a platykurtic kurtosis, which means that most of the scores are towards the bottom of the distribution. So pretty much everyone in the distribution got kind of a low score. So you have mesokurtic, which is most symmetrical. You have leptokurtic, which means more scores are collected at the top of the graph. And you have platykurtic, which means most of the scores are towards the bottom of the graph. So that is basically skewness and kurtosis in a nutshell. Now that we've familiarized ourselves with the basic graphing concepts, let's take a look at some examples of these graphs. Some common types of graphs used in statistics include frequency polygons and cumulative frequency polygons. These should sound familiar because we learned how to calculate frequency and cumulative frequency with Princess Ariel last week. Additionally, we have graphs called histograms, bar graphs, and lastly, stem and leaf plots, which, to be perfectly honest, nobody really ever uses. So let's talk about each one of these in a little bit more detail. A frequency polygon shows the scores on the x-axis and the frequency that that data point occurs on the y-axis. So it'll look something like this. Along the x-axis, you can see scores from 35 all the way to 175. And along the y-axis, you can see how many people received that specific score. Similarly, we have the cumulative frequency polygon, which allows you to plot the cumulative frequency instead of regular frequency along the y-axis. And if you remember, when you calculate cumulative frequency, you always reach 100%, which is why the graphs or the polygon for cumulative frequency will always go up and it will never come down. The second type of graph we'll talk about is a histogram. Histograms are typically used to show quantitative and numerical data. So for example, if we look here, along the x-axis, we have the number of hugs Olaf gives per hour. Along the y-axis, we can see the number of people receiving the hugs. So if we look at this histogram, it looks very similar to a bar graph. The only thing is that we actually connect the bars to each other so that ultimately you can draw some sort of a trend line encompassing all of the data. So in this case, if we look, we could see that the most people, right, about 12 people got 4 hugs from Olaf. And we can see that the fewest number of people who received hugs from Olaf was when he gave 0 hugs and when he gave 12 hugs. So it sounds like between 3 and 4 hugs is the amount of hugs people want to get from Olaf. Poor Olaf, he loves giving hugs. The third type of graph we'll talk about is a bar graph. A bar graph is used to compare groups and show changes over time. So for example, if we take a look at this graph, we can look at favorite songs from Frozen. We have In Summer, Olaf's song. We have Do You Want to Build a Snowman? Into the Unknown. Wow, that has almost 100 respondents who love that song, who say that that's their favorite song. Not really a surprise because it came out in my second movie, which was definitely a little bit different from the first Frozen. We can see that Poor Let It Go has been so played out that it has become everyone's least favorite song. However, the point of all of this is that a bar graph can show us how many people prefer which type of song. The last type of graph we'll talk about is a stem and leaf plot. The stem and leaf plot is a special table, really, where each data value is split into a stem, the first digit, and the leaf, the last digit. So for example, if you have a stem of 4 and a leaf of 0, that means the data point would be 40. If you have a stem of 4 and a leaf of 9, that score would be 49. So stem and leaf plots allow us to see which range of numbers occurred most frequently in a really quick way. So that concludes the different types of graphs that we're going to learn about. I think it's time for us to try to do an example together. In order to reduce the fear of the people of Arendelle, I decided to teach classes about my magic. I thought that if they understood how they could possess magic, they might be more accepting of me and my abilities. I currently have 30 students who are learning how to use magic, and like in all classes, we recently had a quiz. Here are the data from that 50-point quiz. So this may look familiar to you from last week's lecture. The X represents the score that the students received, and the F represents the frequency with how often that score occurred. So by looking at this data, we can see that the score of 46 occurred 1 time, the score of 33 occurred 3 times, and the score of 23 occurred once. So let's imagine that I want to practice constructing a frequency polygon, a cumulative frequency polygon, and a bar graph with these data. What should I do first and where do I begin? Well, the first thing I would do is construct a frequency distribution with the cumulative frequency scores. You cannot construct a cumulative frequency polygon without having cumulative frequency in your distribution. So if this is the data that I started with, the first thing I'm going to do is convert this into one long table of data, which is the beginning of our frequency distribution. I'm going to make a separate column for CumF. CumF is my cumulative frequency. And if you want more information on how to calculate cumulative frequency, please visit Princess Ariel's frequency distribution lecture, where she tells you all about how to do that. So once you've calculated your cumulative frequency, remember cumulative frequency starts with the largest number of data points you have. So 30 students participated in this magic quiz, so 30 is going to be the top score in the first line of the cumulative frequency. 30 minus 1 gives me 29. So all I'm doing is I'm subtracting the frequency from each cumulative frequency as I move down the line. For example, I have 30 as my cumulative frequency. 30 minus 1 gives me 29. 29 minus 2 gives me 27. 27 minus 0 will stay at 27. 27 minus 2 brings me to 25. So on and so forth all the way down the line. Remember, frequency tells us how many people or how many students got that particular score on their quiz, but cumulative frequency tells us how many students got that score and everything below it. So in other words, if I look at the score of 43 and I want to know the cumulative frequency for the score of 43, I can say that 27 students got at least a 43 or below. So remember, cumulative frequency and frequency answer different questions. In any case, the whole purpose of why we're doing this is to construct a cumulative frequency polygon. So now that we have all of our values, we are ready to plot them on our graph. Let's start with the frequency polygon first. What we need to do is place the scores on the x-axis and the frequency on the y-axis. Something that we need to consider is the idea of those intervals. Remember, the intervals need to be equal, and we should also be wise about the increments that we want to use to plot on our axes. So given that our largest quiz score is 46 and the smallest score is 23, I think it might be a good idea to use intervals of 5. So maybe we'll start from 20, 25, 30, 35, 40, 45, and 50. So your x-axis will be in increments of 5. Our highest frequency, if you recall, is 3. The lowest frequency we have is 0. So I don't think it gets easier than that. I think we can plot those in intervals of 1. So all that is to say that this is what the construction of our graph would look like. On the x-axis, you have the quiz score ranging from 20 to 50. And along the y-axis, we have frequency ranging from 0 to 3. So far, so good. Now that we have our graph set up, we need to plot the data points. Starting at the top, what we're going to do is we're going to find the score on the x-axis and then the frequency up on the y-axis. So you're going to go across and then up. The first score that we see that we need to go across for is the score of 46. 46 is going to be closer towards the end of our x-axis because the maximum there we have is 50. So you're going to put your finger on 46, the placement of the number 46 along the x-axis. From there, you're going to look at the frequency. How many times did the score of 46 occur? We can see that 46 occurred only one time. So from your finger on the x-axis, you're going to go up to the number 1 along the y-axis and plot that dot there. The next thing we're going to do is plot the score of 45. We can see that the score of 45 occurred twice. So we're going to put another dot at 45 and go up to the number 2 because it occurred twice. You're going to do this for every single score in your distribution. And once you continue doing this for all the data points, you should have a scatter plot of different points through which you are going to be able to draw a line, essentially connect the dots. When you do that, once you plot all the frequencies and you connect the dots, your graph should look a little something like this. So this is your frequency polygon. If you were to draw a curve over these data, would you say the data are skewed or not? And if the data are they skewed positively or negatively? Remember, when you identify something as positively skewed, the tail is on the positive side, meaning more scores are concentrated towards the lower end of the spectrum. However, if something is negatively skewed, that suggests that the tail is on the lower end of the spectrum and majority of scores are concentrated on the positive side. So by looking at this, does the data look like it is skewed? Additionally, what can you say about the graph's kurtosis? So a good way to answer this is to draw this line around the data. Can you identify the center point? Does it look like a normal curve or does it not? Does it look like more scores are concentrated above the center or does it look like more scores are concentrated below the center? So it's often helpful to give yourself an idea of where those center lines are. If we look at the line coming down vertically at around the 35 point line on the x-axis, that would be a good way to split the graph in half to check for symmetry. Does it look like there's the same amount of data points to the left side of that split as there are to the right side? Based on what I'm seeing, it looks like more data points occur on the right side of that split. So that suggests that most of my students did better on the magic quiz than they did worse, because their scores are higher. If most of the scores are aggregated around the higher end of your x-axis, that would suggest that your graph is negatively skewed. We can see that the tail is in the direction of the lower scores, 20, 25, etc. If the scores were low, that means that they did poorly on the magic quiz. However, seeing this graph makes me feel better because I can see that majority of my students actually scored higher on the positive side, suggesting that the skew of this data is negative. Now let's talk about kurtosis. If you take a look at the second line that I've drawn directly through the center, but now it's going horizontally, this is going to help me look at the scores above the line and below the line. Remember, kurtosis refers to how flat or peaked a graph is. Here we can see that we have almost the same amount of scores above my dotted line as we do below the dotted line. So if the scores are pretty symmetrical on top and bottom, we call that mesokurtic, suggesting that it is not platokurtic. Most of the scores are not low. It is not leptokurtic. We don't have super high peaks. We would say that this is mesokurtic because the scores are distributed evenly above and below the kurtosis line. So now we need to plot cumulative frequency. Remember, for plotting cumulative frequency, we're going to use the CumF column of our data instead of the F column. We've already plotted frequency, so now we need to focus on the cumulative frequency column. If we think back to the largest score we have on this quiz, that stays the same. The largest score we have is 46, and the lowest score we have is 23. In that case, we can use the same increments of 5 to plot the x-axis. However, what changes now is the cumulative frequency values. We can see that the largest cumulative frequency number we have is 30, because there are 30 students in my class who took the quiz, and the smallest frequency we have is 0. So what we need to do is change the increments that we have for the y-axis, but we can keep the x-axis the same. Just to keep spacing in consideration, I'm going to choose increments of 10 for the y-axis. So 0, 10, 20, and 30 for the cumulative frequency, and I'm going to have my increments of 5 for the x-axis for the scores. So the first thing we need to do here is take the score of 46 and plot the cumulative frequency that's relative to this score. So remember, the score of 46 is what we find along the x-axis, and then you're going to bring your finger all the way up to 30 because 30 is our cumulative frequency, and you're going to place a dot there. The next score we have is 45. So you're going to put your finger on 45 along the x-axis, and you're going to slide your finger up to 29 because our cumulative frequency there is 29. Moving on, you have a score of 44 that has a cumulative frequency of 27. So all you're going to do is continue plotting each cumulative frequency on the y-axis for each score which is found on the x-axis. Once you plot all of the cumulative frequency along the y-axis, this is what your graph should look like. Remember, with cumulative frequency, the graph will never go down because it will always stop at 100%. Cumulative frequency represents how many people got that particular score and everything below it. So in this graph, we could see that the progress is fairly gradual. And this is your cumulative frequency polygon. The last thing we're going to do is create a bar graph from the same frequency data. So a bar graph can be horizontal or vertical. If you want to keep your bar graph horizontal, you're going to plot the quiz scores on the left-hand side of the graph and the frequency along the bottom. So it'll look something like this. Typically, we were used to plotting frequency on the y-axis. In this case, the quiz score will go on the y-axis and the frequency will go on the x-axis. However, if you want to keep your graph vertical and keep things similar to the way we've been doing frequency polygons, then you would you would keep things in the same place. You would plot the quiz scores on the x-axis at the bottom and plot the frequency on the left-hand side on the y-axis. So both of these are examples of bar graphs, and both of these would be acceptable if you were asked to create a bar graph from a frequency distribution. You may also notice that the bar graph on the right, the one that resembles your frequency polygon, can also be considered as a histogram if you reduce the space between the bars, similar to that graph I showed you of Olaf's hugs. The only difference would be that you would remove the spaces between the bars and draw a trend line encompassing all of that data to once again see that similar shape curve. So hopefully that was helpful for you in understanding some basics of graphing and how you can start creating your own graphs on your own. Remember, the most important thing when it comes to creating graphs is to make sure that you are using the proper intervals for your x and y axes. Using the wrong increments and wrong intervals can create data misrepresentation, inflation, and even data fraud. And nobody wants to be a victim of that. Thanks so much for tuning in and watching this lecture on graphing data. I hope it was helpful for you, and I hope to see you again on Once Upon a Lecture.